Okay, so of these problems, the ones that we've done from the last couple of days, because we missed yesterday going over homework, which ones do you want to go over? What things can I help you with? 41? Can do, maybe. Either one. Anything we haven't covered that has been assigned. Does that make sense? Sure.
Okay, 21 part B.
21 part B, sure. Yep. Anything else that you want me to put on the list?
Oh, number 30.
30 is on, yep, I got it. No, that's perfect. It's all good. Okay. Anything else? 14. Sure. All right. Shall we start there? If we have more questions, we can do it. These are all chapter 7, correct? Just want to make sure I'm not confusing myself here. All right. So we'll start with 21. We'll just kind of go through chronologically in the order that you did them. So number 21. Okay, so this was the one with the sets of boxes resting on the table. And did we just want to go over one part of it or both parts? Just part B? Okay, so part B just says that they want to rank the normal force exerted by the bottom block on the top block. Okay, so this question honestly is very straightforward, but a lot of people, especially smart people, overthink it. Okay, so I'm going to just draw a picture of one of the towers of blocks. So here's 1.4 kilograms, and this one is 1.0 kilograms. Sorry, my handwriting is atrocious today. Oh, you're frozen. You can't see anything. Sorry. There are my cute little boxes. Is that better? Okay, if we just focus on this block, the 1.0 kilogram block, the one on top, tell me the forces acting on the 1.0 kilogram block. Force of the earth. Awesome. Which way does that go? Yeah. Indeed. As always, right? F earth on the 1 kilogram, we'll just call it. Anything else acting on the 1 kilogram block? The box underneath. Which way is it going? Up. F block on the 1 kilogram. Anything else acting on this 1 kilogram block? Nope. What's the net force on this 1 kilogram block? 0. And you know that because it's not? I heard somebody say accelerating. Yeah, it's not accelerating. So can you tell me how big this is? Or let me back up. Can you tell me how big the force of the earth on the block is? 9.81 newtons, because it's 1 kilogram times 9.81 meters per second squared. Yeah? Yeah, that's clever, right? So this force up here has to be 9.81 as well. Yeah. So then if you've got one block that's 1 kilogram, one that's 1.4, and one that's 1.2. Yeah. The one. The other way around. Yeah. Does that make sense though?
Wait, what did you just say?
Say it again, Janelle. What'd you say?
The one with the most mass would be the one with the most normal force.
Yeah. So I'm thinking, and I may have written it down wrong, so let's just make sure that we agree. Because B has a mass of 1.4, that it's going to have the greatest normal force acting on it. And then C has the next one, and then A has the smallest. Is that okay?
What I did was
I was confused.
I mixed up the blocks.
Well, because it said the bottom block.
Right. It's the force of the bottom block on the top block.
Oh, the force the bottom block uses that gives it the top block.
Yes, they're looking for this force here.
Okay, so I did the bottom block.
Yeah, me too.
Matt is not happy. Talk to me.
It was a confusing question.
It's a thinker, right?
Mm-hmm.
It's a thinker, but once you get there, you're okay. But let's keep going. Hold on, I'm trying to read Maddie's mind here
We're
quick.
taking the mass
Uh-huh.
times the negative 9.81 of the top block or the bottom?
Top.
Why?
Because so here's my stack, right? I'm just gonna back up to my stack real quick.
Oh wait, I get it, because now that's the bottom block, and then the top one is whatever that other one's pushing up on. I don't know. Sure. It makes sense in my head, sort of.
It makes sense in your head, okay, now ish. But there was another question. Did you have a question for us?
I just asked if there were part A or part B.
This is part B.
Yeah.
This is part B. So BCA is the order for part B. Part A, it's the table on the whole thing. All of them have the same total mass of the stack, right? So that's where that's coming from. So life is okay? Sweet. Okay. And hopefully I wrote that down correctly up there. BCA, did I? Sweet. Okay. 27. There's a question on 27. 27 says,
Just the part, the second question about the action reaction.
yeah, that icky word, right? And so is it a force pair is really what they mean. Okay, so it says, consider two forces acting on a person who stands still. The downward pull of gravity and the upward support of the floor.
So no.
To the action, to the pair? Is it a pair? Gravity and the normal force? Is it a Newton's third law pair? That's what I meant to say. True call. Good call. It is not a Newton's third law pair. So 27, so you have the little guy. Oh my gosh, the picture's going to look a whole lot like this picture here, isn't it? Yeah, the floor is pushing up. The earth is pushing down. They're equal in magnitude, opposite in direction, but they are not a third law pair because they both act on that guy. Yeah. Does that get us where we need to go on that one? All right. All right, so we're done with 21, done with 27. Let's look at number 30. 30 says, if you step off a ledge, oh dear, don't do that. You accelerate noticeably towards Earth. Does the Earth accelerate towards you? I'm just asking the question. I don't know.
I don't know. I said
It seemed no.
All right, let's draw. Oh, is this number 30? So here's, oops, that's not a person. That's a snowman. I must be thinking. Okay, so here's my ledge on the Earth, not drawn to scale or circular even. Okay, I put lotion on my hands until they're like slippery. All right, so I've got this person. Here he is. Tell me what forces are acting on the person. The Earth, right? Force of gravity, the force of the Earth. It's pulling which way? Down. So this is the force of the Earth on the person. Is it causing the person to accelerate? Indeed, it is. What's the Newton's third law pair force that goes with that one? Force of the person on the Earth. Where does that one go? It goes up, right? If I can get my silly thing, my technology is just a happy deal today. Okay. Force of the person on the Earth. Which force is bigger?
Same, duh.
They're the same, right? It's a Newton's third law pair.
Over the mass.
Forces are the same, but are the masses the same?
No.
Indeed, they're not, right? My mass is a little bit smaller than the mass of the Earth. A little bit, right? And so, which one's going to accelerate more? Me. But is the Earth going to accelerate? Absolutely, it will.
I did say it does.
It's weird. You
It
did
said-
say,
Yeah.
yeah, like not much. So if I drop, like, everybody, I want you to like feel the Earth, okay? Do some like, feel the Earth below your feet. Okay, I'm gonna let the frog go. Are you ready? Here we go. Did you feel it? It accelerated up. Did you feel it?
No.
I probably didn't. You want to know why? Because I called my physics teacher friend that was on exactly the opposite side of the Earth, and she did the exact same thing at the exact same time. No, not really. But I could, right? You could imagine that all of the physics teachers in the entire Earth, on the entire Earth, are dropping their frogs at exactly the same moment. And so the Earth is accelerating in all these different directions at once. Are you with me there? Yeah?
That's why it does it?
No, it's just because it's got a huge, huge old mass.
I just don't.
You don't believe me?
It makes perfect sense.
I just don't.
It just
get-
gets
It's hard. It's right.
Well, the thing that I don't get is like if you're skydiving,
Mm-hmm.
Getting a formula. for
technically you're saying that the ground would be accelerating towards you.
It is.
But
Let's do the math, you guys.
no, we don't.
No, we're going to do the math because I want to. F of the Earth on you. So it's going to be the mass times negative 9.81 meters per second squared. Yes? Okay. Let's pick a smallish mass. What do you think? I was thinking like, on the order of maybe 100,
3.
30, whatever you want it to be. I mean, okay, let's do the frog. Let's do the frog because we were talking frogs before. Okay. So the force of the earth on the frog, let's say he's a kilogram. He's not really, but that's going to make it easy. Okay. You can figure out then the force, right?
Yeah.
Okay. The force, I'm going to change this to frog, of the frog on the earth. Okay, so let's do the math here just because we can and it's easy. If this is a kilogram, let's just do it. What's the force going to be? 1 kilogram times 9.81 meters per second squared. 9.81, right? Newtons. So the force of the frog on the earth is 9.81. Is going to equal its mass times its acceleration. Are you okay with me saying that? Or you can say, if you like this better, A is equal to F over M. I like that better. Okay. I think that's right. I'm going to look it up though because I can't remember for sure. Let me just look it up real quick.
This is like the most important equation ever.
Ever.
Like I swear we use it all the time.
Right?
I used to look at it as like such a simple equation.
I was right. Sweet. My memory holds for once. 6 times 10 to the 24th kilograms is the mass of the earth. I want to know the acceleration. I know I told you it was big.
Wait, is it 6.10 to the 24th, the mole?
That's 6.02 times 10 to the 23rd. So there is more than a mole of kilograms in the mass of the earth.
Chemistry now.
Avogadro.
That's how I move. Avocado.
Avogadro.
Oh,
So do your math, guys. Get your calculator out. Everybody needs one, right? Let's give me it up. Ooh, Miss Cardinal, you need a calculator. Okay, here you go. Who needs one?
I already have a pretty cool calculator.
It's so sad when you do that it's such an important number. You don't remember that.
Anybody else need one?
Every time my math teacher says get out your calculators, I don't because I don't want her to call on me.
Exactly.
But she still calls on me all the
Silly
She does that.
Miss or Mr. Whoever.
time.
Rats. And then you don't know the number either.
It's like I'm one of the kids that knows the stuff, so why are you calling on me? Call on somebody that doesn't know
Oh, wait,
so they
wait,
can
let's
learn
take
from it.
Wait, I did that wrong. I did that.
So you're going to do 9.81 divided by 6 times 10 to the 24th. Do the math, friends. Instinct, is it going to be a big number or a small number? Really ridiculously small. Yeah, you probably could do it in your head, really. I mean, you're just, it's like it's 10.
Times. I was like, why is it this high?
Gerald, it's nice to see you. It is 10 to the 24th. That's just written poorly. 10 to the 24th.
You didn't even have a negative on what?
What you got? How much does it accelerate? Is it a lot or a little?
1.635 times 10 to the negative 24.
What are the units?
No, I don't know.
Meters per second.
Meters per second.
It's acceleration, right? Yeah. Is that noticeable? No. Now, do you want to know something kind of weird? It's not noticeable to you or me, but there are some physics experiments out there that they're doing like right now. I don't know if you guys have heard of, if you saw anything about, if you heard rumblings about something called gravity waves. 2 years ago, they finally proved that gravity waves exist, and they proved it because there were 2 black holes that collided, and then I may have shown you a video about it, and they collided, and then those waves rippled through the earth, right? In order to measure that, they were measuring little tiny vibrations so small that something like this, if it was very near it, would matter. Is that weird? I mean, that's intense and kind of crazy. We'll go there another day, not today. Sorry. I would love to tell you. I just want to make sure that we stay on topic. Yeah. Okay. All right. Are we okay with that question?
Why is it
Because it's really, really, really small.
So it's a fraction.
Yeah. It's it's like
Yeah, I know what you mean.
0.1, 2, 3, 24 of them, right? Like so little. So yes, you're not going to feel it, but yes, it does exist. It does happen. What's that?
It's raining. Oh, I went outside and my
We all are then.
It's covered in ice.
And the frog. Sorry. I know. I'm not trying to hurt you.
No.
Yeah.
Then how are you seeing?
Guys,
We're
tell a
Whoa.
funny story really quick.
Okay, hold on.
It's really good. We're panicked. We're just watching that, and they were talking about scraping your windshield because people don't scrape their windshield. But one of my friends didn't know that there was someone didn't know that you could defrost your windshield.
Oh
So
my.
they drove from west to their house all the way in North Liberty with their head out the window because they couldn't. They couldn't roll the window.
What?
These are not safe things, friends.
It's not. It's actually illegal, so don't do that. I thought it was really funny when they said that, and we were like, you know, there's a defrost button.
But wouldn't you scrape it too?
No, they just didn't know that you could do that. And they were freshmen, and also it was their first time driving in the winter. It was just funny though.
Yeah, this is why I'm not going to go home while you guys are all on the road.
This is why I was scary letting 14-year-olds drive
And we
everywhere.
live.
All right, one more thing. Yes, go.
This is just a really dumb thing, but this one time my friend was talking to me and she was saying like, my radiator went out or something like that.
Uh-huh.
And I was like, oh, I don't really use my radiator at all.
What's a
And she was like, you mean your heater?
Oh,
What's a radiator?
well,
Yeah, I didn't know.
I mean, it depends.
Oh, okay.
It, yeah.
Kind of
Oh,
runs your car.
yeah, yeah. All right.
Oh.
We got some palindrome numbers to do still. 14 and 41. 14. Okay. We got stuff to do today, guys, so I need you to listen. 14 says, why don't the enormous number of interatomic forces inside a baseball accelerate the baseball?
Yeah, that's what I thought.
I think that's what I said too. Hold on. I said something about like it has to be acted on by an outside force, but I guess that I don't know if that was one.
It does. It totally does. Okay, so let's talk this through, guys. So, ladies, could you please be quiet so we can talk? I mean, even if you understand this, then just sit tight, please. Okay, so inside the baseball, are there forces that are acting inside it? Absolutely. Millions of them, trillions of them. Like you can pick whatever Indians of, like you can pick whatever. It's a lot of forces. This little thing is pushing this way and this way. But what's the net force of all of those forces? Zero, right? I've got one molecule here and I've got one molecule here, and they're pushing apart and they're pulling together. But this one's pulling this way, this one's pulling this way. The net force between those two is zero, right? So the net force within that baseball is what? Zero. In order to accelerate something, you have to have an outside force. So you have to take something that is outside the system that you're talking about, okay? And that's what's going to accelerate it, okay? That's also in the cart and horse thing that we did at the very end yesterday, when the horse was trying to be all smart and say, I can't get the cart to move, right? It depends on what you're looking at. If you're looking at just those two things, the cart or the horse pulling on the cart and the cart pulling on the horse, those are equal. And if you look at that whole system, then those are equal. But there's other things going on too, right? That's the outside stuff. That's why we care. Did I see a hand? Yeah.
What is internal forces?
What are internal forces? Internal just means inside. So
Do you mean like protons and electrons?
it can be. Yep.
Any given atom is moving unless it's at absolute zero, which is not
Indeed.
possible. So every
And all of the electrons are moving and all of the proton, yeah, everything is moving. Yeah, yeah. Yes. So there's all kinds of motion, all kinds of forces. Depends on which level you want to look at, but holy bananas, there are lots of forces. And we're just talking about anything that's outside of them, like my arm, right, would affect it. Is that okay? Sweet. Last one was 41. People want to talk about 41? Okay, since a force acts on a cannonball when a cannon is fired, excuse me, let me start over. Since the force that acts on a cannonball when a cannon is fired is equal and opposite to the force that acts on the cannon, does this imply a zero net force and therefore an impossibility of accelerating the cannonball. So the same kind of question, right? The cannon and cannonball question is basically the same as the cart and horse question. It's just like the, next step up or whatever, right? Can a cannonball be fired from a cannon? Yes. If it couldn't, we wouldn't know what they are, right? Okay, the only reason we know that what cannons and cannonballs are is because they separate when there is a force inside that pushes one way, right? The cannon pushes on the cannonball and the cannonball pushes on the cannon, right? Yeah. Is that okay? Is that making sense? Okay. Issues, questions, concerns right now? Okay. How are we doing with our time here? 24. Okay, we got time. We're in good shape. Okay. Ready to move on? That was chapter 7. Chapter 8 and chapter 7 are like this. I think they should be one chapter, but he wrote them in 2 different chapters. Yeah. I like a lot of what this author does, but not everything, as you may have gathered already. Okay. Today we're going to do a lesson in marketing. Right? This is Miss Carveling does marketing, so it's going to be really physicsy. But let me share with you what I know about marketing. Okay. How do you feel about that? A net force causes an acceleration. Think that's true?
Wait.
A net force causes an acceleration?
Well, part of an acceleration.
This is not supposed to be a trick question.
No, I agree.
If a net force is acting on something, what will happen to it? It'll accelerate, right? Yeah? We've been talking about this for a long time. Last year we talked about this, right? We've been talking about this for a long time. This is part of Newton's first and second law, right? If there's a net force, then it will accelerate. If there's not a net force, it won't accelerate, right? We can kind of distill that down into net force causes acceleration. This is not a surprise, okay? We know how big the acceleration is because acceleration is equal to F net over m, right? Okay? This is nothing new. This is old stuff. You got this. You've mastered this. No problem. Or at least you kind of convinced me that you mastered it. How many of you, when you've gone into a store to buy a certain product, like let's say toothpaste, it always comes to mind, or your favorite shampoo, or, a box of butter, whatever you're going to go to buy, you have this list, right? And you're just looking for this specific looking product with, the red box or whatever. You walk in and you're searching the aisle, you're searching on the shelves, you can't find it anymore. Not because you overlook it, but because somebody at the company thought it would be a great time to change the look of the box. You know what I'm talking about? Like, I always get the blue toothpaste, and now the box is green and purple. Like, who does that? They're confusing me, but they do that. You know what I'm talking about? Okay? That's all that chapter 8 is going to do.
It's changed the way you look.
It's just new packaging. New packaging of the same thing. Okay? That's what I'm talking about. So this is what we know. This is what you're used to going to the physics store to see, right? Net force causes acceleration. Life is good. I'm going to show you the new package now. Okay, it's not scary. Well, maybe it is. I don't know. We'll see. Here it is.
Whoa, I don't like this one.
Whoa! Oh my gosh! You don't like the squares? You like the circles better?
No, I just don't like the mini
What is that word?
Right? I know. Let's figure it out.
Pmomentum.
Here we go. So you want to write this one down. This is the new one. This is the one we have to figure out what in the world's going on. Because Carveling is telling you that you understand this already. And you're like, don't think so. But I'm going to tell you right now, you do understand this. Just you need to know what the words mean. Okay, here we go. So let me write it out in nice handwriting here. So impulse. What's impulse? Oh.
Wait, is there a P in front of momentum?
Yeah. Causes a change in momentum. It's silent.
You're telling me there's always been a P in front of momentum?
Yeah.
These American languages are so
No. This is
It sounds right. English is crazy, right?
You guys do this. I'll say these words.
I know.
All right.
just we don't know.
So impulse causes a change in momentum. Impulse causes a change in momentum. So the first thing you need to know is what in the world is. Let's start with impulse because that's the first one. We'll get to momentum. We'll do them both today, I promise. Impulse is kind of I mean, it's not,
Spell momentum.
yeah.
I feel like people write it differently.
Oh, well, that's the way you spell it.
No, I'm not saying
Is that the proper way to spell momentum?
Yes,
Really?
yes. So impulse. Why won't you go? There we go.
You learn new things every day.
I know, that's why you come to see me, right? Right. That's what I'm talking about. All right. An impulse. Let's talk about what an impulse is. Have you heard the word impulse before?
Yes.
Yes. I've heard it in terms of marketing a lot. I think about it when I'm walking towards the cash register at, what's that? Yeah, at Trader Joe's, right? You have your cart full of everything that's on your list. Life is good. And then as you're walking up to the cash register, what do you see there? You see those little like boxes of chocolate?
Let me see.
That's not on my list of things I need, but I really want it, right? There's, what else do I see? What do you see?
Another box.
Another box, like lots of boxes of stickers.
That's
Reese's.
why
That's why they put it all there, friends. You guys, this is like good marketing information here. You always have that list and you get all those things. You get your milk and you get your butter and you get da-da-da-da. And then, do you need those 3 boxes of Reese's? Those 3 boxes of Snickers? Those 3 boxes of whatever? Absolutely don't. But there's something that pulls you. Are you with me here? It pulls you this way and you're like, oh, it's just one little thing. Are you with me there? Yeah. Oh, but then there's chapstick. Oh, it pulls me there. I'm going to just grab that real quick. Right? I'm just going to get that. And then you have like 7 extra things in your cart.
That's what always happens at Costco.
I know. Impulse shopping. Okay. Come back to me. That is called impulse purchasing. When you go into marketing, friends, you will learn that, right? People get paid a lot of money to design those shelves and those setups the way they do so that things are just at eye level. And you're like, right? And they put those nice like coolers with the beverages, right? They're like, oh, I could go for a really, just an ice cold Coke, right? Like that would be great on the drive home, right? Like you know what I'm saying? They do this. So let's think about this, guys. It's applying, it's changing, it's pulling on you. Are you with me there? It's pulling on you. It's just a quick thing, right? It's just a quick little, oh, I'm just going to go grab that. Okay? That's what an impulse is, and that's what it is in physics too. Okay? It is. It's a force that acts over time. Okay? So it can be one of 2 things. Well, I guess it could be anything, really. So it could be a really, like a force. It's like, oh, I need that chocolate, right? And it's just really quick, right? Or, as Tatum was describing, it could be walking through Costco, right? Sometimes I go to Costco and I have like 2 things. Like I just need to get eggs and diapers. Like that's it. No, you don't. Because then you see the, I don't know, whatever else, like, you're like, oh, yeah, and I totally, and yeah, right? It's a force that acts over time. It can be a long time or it can be a little time. Usually, the marketing people think of it over those quick little times, right? Because they just want to get you to get one more thing, okay? Life is okay? Okay, that's what impulse is.
Or when you go to the store like Walmart and they have all the sales every Wednesday, everything goes lower, and then you're like, oh, it's only a $6 shirt. That's good.
Whatever, right? Like no big deal, right? Impulse purchasing.
And then
You with me there?
you might never wear one.
All right. Sad stories. Momentum. Momentum is, I think this is the funniest quantity that exists. Momentum is a quantity that physicists made up because cool stuff happens with it. It's a quantity, it's a product of 2 numbers that when they made observations about things, they're like, oh, that thing like stays the same sometimes. That's kind of interesting. Let's call it something. Well, what are we going to call it? Let's call it momentum. Why not?
Some sort of Latin.
I mean, you can spell stuff however you want, right? Momentum is the product of mass and velocity. Okay? Momentum is mass times velocity. So let's think about this just really kind of on a broad scale. I'm claiming that you know what this is, and I'm gonna show you that you do in just a second here. Force acting over a time, we're okay with what that means? Okay? Momentum is mass and mass times velocity. My claim is that this is something that you've seen before, that it is this. Are you ready for me? This is gonna be a good little moment here in time. Here we go. So excited. Here it comes. We're gonna write this out with some mathematics here. Force, what letter do we use for force? F. And it's acting over a time, so we're gonna multiply it by time. Force times time. Okay. The implication of this statement is that the force times time causes or equals a change in momentum. Change in means something. It means that it doesn't stay the same. Now, yeah, so we're gonna have a delta in there. You got it, you got it. Now I'm gonna put the delta in there, and some people are gonna be happy, and some people are like, no! So I'm gonna write it both ways, okay? The triangle thing, yeah. So I'm gonna write it both ways, so I don't want everybody to freak out. But so we can say it's mass, oops, excuse me, I did that poorly. The change in mass times velocity, okay? So we can write it like that, but some people don't like that delta. Some people are like, sweet, I love the deltas. And they're like, no, get away. Generally, not always, generally, and in most of the problems that we're going to do in this classroom, as things happen, as forces are applied to objects, which thing do you think probably will change? The velocity. Most of the time, not all the time, but most of the time, the mass is going to stay the same. So I'm going to rewrite this, and I'm going to say that force times time is equal to mass times. So I can write it as the change in velocity, or for my friends that are not super excited about that delta, I'm going to write that as final minus initial. Is that okay with everybody? What just happened there? I'm just literally taking the change in and writing it as what it is and making it true. How you doing so far? So you went to the physics store, you saw you were looking for net force causes acceleration. That's what I wanted to go see, right? That's what I was expecting. I see this other crazy town thing with these words that I don't know what they are. But are you ready?
Ready.
Here we go. I'm going to divide by time on both sides. We okay? So far, so good? I'm not going anywhere. Just want to make sure people don't think I'm breaking algebra. I'm also going to divide by mass. I'm just going to do it all in one fell swoop. And then I'm going to rewrite it because that's a huge mess of craziness happened there. And then I'm going to wait for a minute. See how we're doing. Cool. We're going to get there. So I'm going to gaze over at the board over there until you all gaze with me. Make an observation that will be helpful.
Acceleration.
Oh.
It's equal
What the heck?
due to substitution.
What? What? What are you so excited about, Janelle? What's so exciting there?
It's the F net equation.
Oh,
That's crazy.
right?
Which is also equal to the other acceleration.
Yeah.
So therefore, VF divided by VI, or VF minus VI divided by T equals acceleration. Wait,
You just blew my mind.
there's another equation that it matches.
I just said that.
Oh.
Are we okay?
Basically, you just took those two, took the accelerations off
And
and equals
substituted.
it.
Smashed them. Yes. How are we doing? Are we okay?
Yeah.
Yeah? Okay. I think I think. I'm gonna check this out real quick because I want to make sure. Swapping. Let's see, you're up here. You need one more. Well, no. You know how to find momentum, right? Mass times velocity. And you know how to find impulse, force times time. And the last thing that I just want to make sure you know is that force times time equals mass times change in velocity. Now you can do your homework for the weekend. It's going to be a nice, wonderful, lovely weekend. How cool is that? I ended like with a moment to spare. It's miracles happen some days, I suppose. You guys, I hope you have a really, really lovely time tomorrow. I hope that you learn a lot. I hope you have a really lovely. We do not have school Monday, so I have a nice long weekend because it's ML King Day. So it's an opportunity for people to have a day of service. Yeah. So don't get lined up. Just sit tight.